A very useful thing to have when creating geometry objects or modifiers is the ability to raycast, and that is the ability to take a point and cast a ray from it into some kind of direction and see where it hits some object or some other mesh. And this is something I want to explore in this tutorial by creating a tool that will essentially take a mesh and project it onto another mesh without altering its topology. So as an example, let me just create a sphere, and I'll create a small sphere, and then on top of it I'll also create a teapot, and then I'll place the teapot over my sphere. And what I want to do is take every single vertex of this sphere and project it along its normal until it hits the inner boundary of this teapot. And I want to record the position where it hits it and use it as the new position for that vertex while keeping the original sphere's topology. So this will essentially take the sphere and project it onto this teapot from the inside. So let's get started by taking our sphere and throwing the lab geometry modifier on top of it, and click edit plugin to begin editing our plugin. First thing I will do is change the type of the first input to polygon mesh, and this will be the input I'll use to select my outer mesh, or the mesh I will be projecting onto. The inner mesh is this original input, which is our base object. In this case it's a sphere, but it can really be anything else. So I will be producing a polygon mesh as a result, so I'll just use a polygon mesh constructor here, and I really want to keep the polygon or the topology of my original sphere, so I'll just drag out my source mesh and just put the polygons into this polygon slot of our output mesh. I will not be changing that. What we will be changing is the vertices, and for this we'll be creating a special graph. So let me create a graph that will modify the vertices of the original mesh by projecting them onto this outer mesh. So I'll go inside my graph, and we will definitely need the vertex position, so I'll create a new input called vertex, and its type is going to be vector3. We'll also be needing a vertex normal, or which direction we want to project this vertex. So I will change the type of this to vector3 as well, because normal is a directional vector, and it also will also be a unit vector, so we don't really need to worry about normalizing it. So the last thing I need is my outer mesh. And unlike this, the input that we added for the plugin, I will change the type for this to a triangle mesh instead of a polygon mesh. And the reason I will use a triangle mesh object is because if we drag out its properties, it has this important output called get volume hierarchy, and this essentially provides a way for us to do things like raycasting and intersection testing in an optimized manner without having to deal with every single phase. It takes some parameters which are currently not initialized, but I will just set the default values to 5 for my minimum leaf size. This is the minimum volume of the volume hierarchy it uses to optimize its algorithm, and I will use 5 for the minimum leaf element. These parameters are not really important as long as you keep them kind of on the low side, but this leaf size parameter really depends on the scale of the scene you're using. 5 is a decent acceptable value in my scenario. So I will drag the properties of this volume hierarchy, and as you can see, it has a method called intersects, which I will use to test for intersection of array with my mesh. So it accepts array, but it also has these two hidden parameters, which are start and end. And this allows me to specify where I want to start heat testing and where I want to end it. I'll just set the start to 0 and end to 200, just so it projects out to some kind of distance. You can probably even create this as a parameter for your plugin, but we'll use fixed values for now. And for the ray parameter, we actually need to create a new ray, which is a special type Ephere geometry ray 3. So I'll just type in ray to create it here. And it has a constructor which accepts an origin and a direction. The origin of array will be our vertex, and the direction of array will be our normal. As I mentioned previously, normal vector is already normalized, so we don't need to worry about doing that. So the output of this ray object I will wire into my ray input for the intersector function, and it produces a output called point of intersection, which is exactly what we need to output from this graph. And this is going to be the point where this ray hits our outer mesh. So if I go out of my graph, we can now wire the values, the inputs of the graph with the rest of our plugin. And for the vertex parameter, we will use the vertices of our original source mesh. For the normals, we will use the vertex normals over source mesh. And because these are arrays as opposed to single values, the output of this graph will also produce a vector 3 array. So for outer mesh, we need to specify a triangle mesh. And because our outer mesh here is a polygon mesh, we need to create a new triangle mesh. And there is a neat constructor for a triangle mesh which accepts a polygon mesh. So we'll just use that to kind of convert our polygon mesh into a triangle mesh and pass it onto our graph. The output of this is a vector 3 array which we can just wire directly into the vertices of our resulting polygon mesh, and we will select the polygon mesh as the result of our whole modifier. It is not doing anything right now because we haven't actually selected outer mesh, so let's do it right now. We will select our teapot, and after we do that, we can see that it produced some kind of result. This is already looking like something being projected onto a teapot, but it's not exactly our teapot, and the reason for that is because it is using object coordinates at the moment, and the object coordinates for our teapot are different than the object coordinates for our original modifier object which we use here, so we'll actually need to take that into account. To do this, let's create a new component input for our mesh. If I right click on this and select that mesh component input, I can add a transformation input, and we can do the same thing for our outer mesh. So this will give us transformations for both our source object and our outer mesh object. And what we want to do is we want to take the coordinates of our outer mesh, and for every vertex we want to put it into the same coordinate system as our source mesh. So to do this, we will actually need to break this up into a couple more nodes. So I will drag out my outer mesh, so just so I can get the access to my vertices of it. And I will create a triangle mesh constructor which accepts vertices and faces. The faces of this triangle mesh will remain the same, so I'll just take the or rather, sorry, I'm not supposed to be doing this. Instead, what I will do is I will create a new triangle mesh here, which will accept both vertices and faces, and I will grab the output of this triangle mesh because we don't want to be dealing with polygon mesh, we're dealing with triangles at this point. So I will grab the triangles of this triangle mesh, and I will wire it into the faces of our triangle mesh constructor, and the vertices between this mesh and this mesh we need to convert into our source object's coordinate system. So first we will need to multiply them by the outer mesh's transformation, and to do this I'll add the multiply alternative to node and select the first input as my outer mesh transform, and then I will multiply vertices of my triangle mesh by that transformation. So right now this result will give us vertices in the world coordinates, and the next step is just to put those coordinates into our source mesh's coordinates. So I'll just add another multiply node, and I'll grab the transformation of my source mesh. So I'll take my inverse and I will put this into this multiply alternative node, and I'll just put this vertices in world coordinates to multiply by the inverse of my source mesh, and the result I will put into the triangle mesh here. So the result of this triangle mesh is now something that exists in the same coordinate system as our source mesh, and we can replace it as the outer mesh for the graph we're using. Once I do that, you can see that if I just toggle on the topology, you can see that it is actually projecting our sphere vertices onto the teapot from the inside. If I go to my sphere and I change the segment count, you can see that it interactively keeps reprojecting my sphere onto the teapot. So this has been a brief introduction to raycasting. There is obviously a lot more things that we can do with it, but we will explore it in future tutorials.